multiply. Multiply two rational expressions. They look like two fractions, and we're going to treat them like fractions, but because they contain variables, we need to call them properly as rational expressions. The first fraction, k squared plus 5k plus 6 over k squared plus 9k plus 14 times k squared plus 7k over k squared plus 5k plus 6. This is the problem at hand. Now, in general, when someone asks us to multiply two fractions, in this case two rational expressions, it's not quite literally that we're going to take these two and multiply straight across. What actually happens, the way I picture it, is we're going to join these two fractions. When two fractions are next to each other, we're going to join them with a one giant big old fraction bar. I'm going to make it pretty big to see, because I'm going to work this problem with an ongoing, we're going to keep this as the fraction bar, keep replacing what's in the numerator and denominator as we go, and we're going to talk about it as we go. Now, when we connect two fractions together with multiply, we're connecting the two numerators together and the two denominators together with multiplication. But because there are multiple terms in each of these numerators, multiple terms, 1, 2, 3 terms in this numerator, 2 terms in this numerator, we've got to capture them in parentheses before we continue. 3 terms in this expression, which, you know, these are also polynomials, because the exponents are whole numbers and positives. So we're looking at whole numbers that are positive. We're looking at 4 polynomials involved in this joined expression. Now, rather than literally multiply with vertical method of multiplication or other techniques like distributive property that we could use, we actually are going to factor. Once we've joined them together, we need to factor each polynomial. There's 4 in here. Factor each polynomial. This is our first step now, after joining them together. So what I'm also seeing, the overall goal here, of course, is to simplify the fraction. When we have fractions, we're obligated to give the answer, the final answer, as a simplified fraction. So that's why we're factoring each of these polynomials. Now, the first step in factoring is to find the greatest common factor. I don't see any greatest common factor in this polynomial or this one or this one. So I'm gonna go, except of course the greatest common factor is positive or negative 1, but since the leading coefficients are positive 1 for each of these 3 that I've underlined in green, we're not going to use the greatest common factor for any of those 3. What I also detect for each of those 3 is that we have positive 1 x squared plus bx plus c type of trinomial. And these, of course, have factoring technique known as, we're going to find the factors of c whose sum is b. The factors of c whose sum is b. 2 numbers times each other that multiply to get c, and the same 2 numbers, if we can find those, that also add to get b, then we're in good shape and we'll be able to factor these polynomials one at a time. Let's begin with this first one in the upper left. C in this polynomial is 6. I'm looking for factors of 6 that would also multiply, factors of 6 that multiply to make 6, but then also add to make 5. Now we know that trinomials come from 2 binomials multiplied together. The easy part of the factoring of polynomials that have this form, where each of these have a leading coefficient of invisible 1, is all we need to make the k squared is k times k. The numbers that we're looking for, factors of c whose sum is b, are going to go in these blanks. It turns out that positive 2 and positive 3 are those numbers. When we multiply positive 2 and positive 3 together, we get positive 6. But when we add positive 2 and positive 3 together, we achieve positive 5. These are the two factors that multiply together to make this trinomial. So we replace this trinomial with its factors. These two factors here. Factors, of course, have multiply between them. Okay, we're done factoring this guy. I don't see that we could factor those any further. Let's move on to this other trinomial with a leading coefficient of 1. This has the same pattern for factoring. Because of that leading coefficient of 1, trinomials come from two binomials. The k squared is formed from the f. This actually makes the f in FOIL. That's where these come from. The f in FOIL, k times k, k squared, k times k, k squared. Here's where the factors of c whose sum is b go. We're looking for two numbers times each other, make 14, that also add to 9, and they're both positives. Okay, positive 14, positive 9. Those numbers, of course, when we look at all the possibilities, are positive 7 and positive 2. When we multiply 7 and 2, we get 14. When we add 7 and 2, we get 9. We replace, it's like slash and replace. We replace that original trinomial down here in the denominator with its factors, and then we move on. Here's that other trinomial that has a leading coefficient of 1. It fits the pattern. In fact, it's the same polynomial, it turns out, as this other one that we factored. So without repeating all the necessary unnecessary steps that we've already performed, the two magic numbers that complete this factoring are positive 2 and positive 3. When we multiply 2 and 3, we get 6. When we add them together, we get 5. Factors of c whose sum is b. We replace this trinomial with its factors. Now, it turns out that the next factor, the next binomial, does have a common factor, the greatest common factor between k squared and 7k. We can actually factor a greatest common factor of k out of these two terms, and what it would leave behind is a k plus 7. In other words, when we distribute k times k, we get k squared, and we distribute k times positive 7, we get positive 7k. So this is the most factoring we can do, is just to take out the greatest common factor, and we replace this binomial, two-term polynomial, with its two factors. Now, all of these green factors are connected with multiply, which allow us to proceed to the next step, and that is that when we simplify fractions, we're obligated to divide out common factors. So that's the second step, is to divide out common factors. This will end up giving us a simplified rational expression by dividing out common factors. So we proceed and compare. I look at it this way. I just start in the upper left of the numerator, and I say, there is a factor of k plus 2 in this numerator. Is there a factor of k plus 2 in this denominator? And I say, yes, there is. The whole binomial acts as a factor in multiply. When I find this entire factor is identical to this entire factor, we apply the idea that anything divides into itself once. These k plus 2's factors individually divide into each other and leave 1's behind. Then I move on to the next factor. I find a k plus 3 in between two times dots. I look for another k plus 3 either at the end of or between two times dots, and here we find it. There's a k plus 3. These are identical factors. Anything divides into itself once. So we replace those k plus 3's with 1. I move on to the next factor in the numerator. We're just comparing factors in numerator and denominator. I see a k by itself, a factor of k surrounded by times dots. It's acting as a factor. I don't see any k's by itself down here in the denominator. This k is locked up with 7, acting together as a factor. This k is locked up with 2, with addition, acting together, k plus 2 as a factor, but no k by itself. There is no like factor like k by itself in the denominator. So we move on. Here is a k plus 7 factor of k plus 7 in the numerator. I find a k plus 7 between two times dots, and because it's an identical factor, any factor divides into itself once. K plus 7 divided by k plus 7 is 1. That's how we would say it. We've identified all the common factors. There's a k left up here in the numerator. There is no k plus 2 that hasn't been already divided out in the numerator to be an identical factor with this k plus 2 in the denominator. So in the end, what we have is, if I can write the result over here, k times all these three ones is k over 1 times this last one times k plus 2 is k plus 2, and we find that this is the fully simplified result of multiplication, and we identify the correct answer as A.